So problem 7 is a problem that we've also went over similar examples beforehand in both lecture as well as the homework. We have a cylindrical mass that's suspended by a cable system. All of those cables are suspended on a ceiling, which is 600 millimeters or 0.6 meters elevated from the point of connection of the three cables. And we want to determine the weight of the actual container. And in order for this to be statically determinate, what we're going to find out is we have to be given the tension in one of the ropes. But I didn't even worry about that part. I just wanted to show you how to set it up, because as I mentioned when we discussed this in the homework, this is definitely something that you're going to see on the exam. So the key point is you need to write 3 equations and 3 unknowns here, your equilibrium equations in x, y, and z. And in order to be able to do that, you have to have expressions for the force, or the force that each of those cables exerts at the point of connection A, which of course is just the tension in the cable, in rectangular components. So the way that you do that is you need to leverage the fact, as we've mentioned a couple times, that forces that are exerted by cables are directed along the cable themselves. So you can capture the direction by finding an expression for the unit vector along the axis of the cable. So the easiest way to find a unit vector is to first get 2 points on the actual line, do tip minus tail in order to write an expression for the position vector, and then you just take the position vector and you scale it by its magnitude. So I set my coordinate system at A, so A is 0, 0, 0, and that's going to be affected because when I actually determine position vectors like AC, AD, and so on, I get them by subtracting the coordinates of D minus the coordinates of A, or the coordinates of C minus the coordinates of A, and so on. As long as the coordinates of A are all 0, basically these coordinates of B, C, and D are going to become my position vectors from A to whatever point I want. Now let's make sure that we can get the actual coordinates of each of these points. Well, first thing you need to notice is they're all on the ceiling. And this kind of specification that we're given in terms of the elevation of A to the ceiling, 600 millimeters, that tells me that the y-coordinate of each of these 3 points is going to be 600 millimeters. They're all 600 millimeters up. Now let's look at the actual x and the z's components. So part of being able to interpret this diagram is noting that if I kind of follow my mouse here, this is an axis that's drawn parallel to z, and this is an axis that's drawn parallel to x. So it's kind of like an xz plane that's elevated up 600 millimeters. So if you notice what this 450 millimeter specification is telling you here, it's that point B, once you elevate by 600 millimeters in y, you need to go in the negative x direction by 450 millimeters in order to get that to that point. So its x coordinate is minus 450. Versus when you look at D, in order to get over to D, what this specification is telling you is that you have to go 500 millimeters to the right. So its x-coordinate is 500 millimeters. And when you look at C, note that it's actually on the z-axis. So what that means is that there's no shift in x. So its x-coordinate is actually 0. So that's how you get the x-coordinates of everything that is 600 millimeters up. Now, how do you get the actual z components? Well, remember that the z-axis is basically once you've come up to that elevation in y, how far do you have to go out in order to be able to get to that point. So you kind of want to start to look for the specifications that are meant to be drawn as displacements in z, either out of the plane or into the plane. And you notice that this 360 millimeter specification, that is drawn from point D to that elevated x-axis. So what that means is that in order to get to D, you have to go out by plus 360 millimeters in D. Versus if you look at point B here, notice that it's actually on the elevated x-axis. So there's not going to be any displacement in z to get to point B. So its z-coordinate is actually 0. D, we already said that's plus 360. What is this 320 going back into the actual plane or the sheet of paper? That's telling you that point C is minus 320 millimeters in z. So that's how I got this minus 320 here. Once you have all of those coordinates, of course, you just need to write position vectors from point A to the point of supports, B, C, and D. The way you get that is you take the individual coordinates of whatever point you're going to, and you subtract them from A. However, since A is the origin of your coordinate system, that's basically just going to create vectors where the x, y, and z components are simply the x, y, and z coordinates of points B, C, and D. So that's how I'm getting this minus 450, 600, 0, 0, 600, minus 320, and so on. Basically, you could show subtracting the 0 in each step, but you're just going to get the same result. Once you have the 3 position vectors, how do you find unit vectors along that position vector in order to be able to express your tensions in rectangular components? Well, all you need to do is take them and scale them by their magnitudes. Of course, to determine their magnitudes, take the square root of each component squared, and I'm sure everyone knows how to do that by now. So once you have expressions for lambda AB, lambda AC, and lambda AD, and it's going to be small numbers, something I hat, something J hat, something K hat, you can express these 3 tensions, TAB, TAC, and TAD, in terms of their magnitudes, whether it's known or unknown, times the x, y, and z components of each of those position vectors. So if you're going to be solving for the weight, you would have to be given one of these three in that problem setup. So you'll know one of these numbers, the other you won't. And then the weight, of course, is purely in the minus y direction. So it is just minus w times j hat. And what you want to do then is write your three equilibrium equations. Sum of all forces in the x, y, and z directions are equal to 0, and set it up where the three unknowns you're trying to solve for are on one side of the equation and all the constants are on the other side of the equation. And of course, you're most recommended to do that in MATLAB. It just helps keep a lot of your math clean and can also make this entire process of computation quite a bit more simple, as I showed in some of the practice videos.